December 30, 1944. A forest road southeast of the Belgian village of Assenois, 2 miles north of Bastogne. The temperature is well below freezing, deep in the kind of cold that makes rifle bolts seize and turns the mud of autumn into iron. The 3rd Battalion of Volksgrenadier Regiment 331, part of General Lieutenant Hans Kurt Hoeker's 167th Volksgrenadier Division, is moving in column through the frozen pines. Hoeker has ordered the attack personally. Adolf Hitler has ordered it before him. The objective is to re-encircle Bastogne, to cut the narrow corridor that General George Patton's Third Army has just punched open to relieve the 101st Airborne Division. These are experienced soldiers. They have survived the Eastern Front. They know what incoming artillery sounds like. They know the whistle of a shell arcing overhead, the crack of a detonation against frozen earth, the shower of rock and frozen mud that follows. What they hear next, they have never heard before. For a moment, there is nothing. No whistle of incoming, no growing shriek of a shell finding its arc. There is no warning at all. There is no whistle. There is no impact against the ground. Instead, somewhere 30 to 50 feet above the column, the air simply shatters. Not once, dozens of times. Steel fragments slice downward from above, through helmet steel, through greatcoat wool, through the pine canopy that the men had trusted to conceal them. Men fall without warning. There is no direction to run, no ditch deep enough to offer any protection. The foxhole that kept German soldiers alive for 3 winters on the Russian steppe is useless here, because whatever is killing these men is not coming from the ground. It is coming from above, and the sky offers no cover at all. In a manuscript later composed in American captivity in 1946, Hoeker would record that his lead battalion was cut to pieces. He described the American fire using the phrase his men had already started using along the entire German front. Hugh Cole, in the official United States Army history of the Ardennes campaign, translated Hoeker's words as tree smasher shells, rounds that seemed to explode against the branches overhead. Hoeker assumed the Americans had learned to time their fuses with impossible precision. He had no other explanation. Neither did the German High Command. Neither did Hermann Goering, who was still insisting in May of 1945 that a weapon of this kind was something Germany was still working on developing. They were all wrong. The shells were not hitting the trees. They were not the product of a gunner who had cut the timing to the nearest fraction of a second. What was killing Hoeker's battalion was a shell with a radio transmitter in its nose, a shell that had been broadcasting a signal since the moment it left the barrel, listening to the echo of its own voice, bouncing back from the ground below, and making a decision, entirely on its own, to explode at exactly the right height above whatever was beneath it. General Hoeker filed his report and never learned the truth. That is the story we are going to tell today. If you care about the men who fought in those frozen Belgian forests, and if you want to understand one of the most consequential secrets of the entire war, take a second right now to subscribe and hit the like button. It costs nothing, and it helps these stories reach the people who deserve to hear them. To understand why those shells left Hoeker and the entire German High Command without an explanation, you need to understand a problem that artillery officers had been trying to solve for 160 years before December of 1944. In 1784, a Royal Artillery lieutenant named Henry Shrapnel began experimenting at his own expense with a hollow cannonball packed with musket balls and a small bursting charge. His idea rested on a simple physical truth. An explosion on the ground wastes most of its energy driving downward into the dirt. An explosion in the air, above its target, sends fragments downward across a wide footprint, striking soldiers on the parts of their bodies least protected by a trench or a foxhole: the head, the shoulders, the upper back. Armies that could reliably achieve that geometry could make each artillery shell several times more lethal than one that buried itself in mud before detonating. The British Army adopted shrapnel's design in 1803. By the time of World War I, every major army on Earth understood this arithmetic. The problem was executing it reliably under field conditions. The only available method was a time fuse. The gunner estimated the range to the target, calculated how many seconds the shell would take to fly there, and twisted a graduated ring on the nose of the shell to that exact delay. If his calculation was perfect, the shell burst above the target. If he was off by even a fraction of a second, the shell either burst harmlessly, hundreds of feet short, or sailed past the target and buried itself in the mud. Powder train fuses, which burned a composition inside a horseshoe-shaped channel, were sensitive to cold, to moisture, and to manufacturing variations in the powder itself. In cold weather, their burst patterns spread unpredictably. Mechanical clockwork fuses were more consistent but still required a separate setting machine to dial the nose ring to the correct delay before loading, a step that on certain British gun types slowed the rate of fire by roughly 25%. Against aircraft, the problem was acute. A fighter or bomber travelling at 300 or 400 miles per hour offered the gunner only seconds of engagement time, during which a time-fused shell had to be set, loaded, fired, and timed to burst within lethal radius of a target moving in 3 dimensions. The British calculated by 1942 that it took over 1,200 rounds of time-fused 5-inch anti-aircraft fire to bring down a single aircraft under representative engagement conditions. The mathematics of that exchange were not sustainable. On the ground, the situation was equally grim. A soldier in a well-dug foxhole was nearly immune to a ground-burst shell. The shell hit the earth, drove several feet into it before detonating, and sent its main fragment cone upward and outward in a pattern that largely missed anyone crouching below ground level. To kill that soldier reliably, you had to score a near-direct hit on his hole. In the forests of the Ardennes, in the island jungles of the Pacific, men behind any kind of cover were protected from conventional artillery by the simple geometry of an explosion that buried itself before it could reach them. What every artilleryman alive in the 1930s and 1940s understood in theory, and what none had been able to execute reliably in practice, was this. You needed a shell that knew, without any instruction from the gunner, when it was close enough to its target to detonate. Not close in an abstract or calculated sense, but close in a direct, sensor-confirmed, real-time sense. A shell with its own judgment. Nobody had a plausible technical path to building such a thing, until a nuclear physicist in Washington was asked to find one. In August of 1940, the National Defense Research Committee, a federal body a few weeks old and led by Vannevar Bush, handed that seemingly impossible assignment to a 39-year-old physicist from Canton, South Dakota, named Merle Tuve. Tuve ran the Department of Terrestrial Magnetism at the Carnegie Institution of Washington. His peacetime work had involved using pulsed radio signals to measure the height of the ionosphere, work that gave him a more precise understanding than almost anyone alive of what happened when a radio wave struck a distant surface and bounced back. Bush gave his group a single-letter designation, Section T. T for Tuve. The task was to design a fuse that could be loaded into a standard artillery or naval shell, and that would detonate the shell automatically when it came close enough to a target to destroy it. No input from the gunner after firing, no timing to be set, no range to be calculated. The shell itself would make the decision. 6 weeks after Tuve received that assignment, a British scientific mission known as the Tizard mission arrived in Washington carrying technical secrets gathered by British researchers. Among them work on proximity fuse concepts by scientists William Butemont, Samuel Curran, and their colleagues at British research establishments. Professor John Cockcroft briefed Tuve directly in September of 1940. That briefing, and the circuit designs Richard Roberts immediately began duplicating and testing at Tuve's direction, became the technical foundation for what followed. Lloyd Berkner, also on the Section T staff, contributed a critical improvement, proposing that the transmitter and receiver use separate vacuum tubes so that each could be independently tuned. That single change made the fuse far more reliable. The architecture it produced was the one that went to war. Other approaches had been tried. Photoelectric fuses that would detect changes in light as they passed near a target, acoustic fuses that would listen for engine noise, infrared fuses that would sense body heat. Every one of them failed in practice for reasons that were obvious in hindsight. A photoelectric cell cannot tell the difference between a passing aircraft and a bank of cloud. An acoustic fuse hears its own passage through the air louder than any engine it is hunting. An infrared cell has no chance against a cold metal aircraft at operational altitude. The Doppler radio approach was the only one that gave the fuse an active, controllable signal to work with, a signal it had generated itself, whose returning echo told it precisely how fast it was closing on a reflective surface below. The core idea was a Doppler radio fuse. The fuse in the nose of the shell would contain a small radio transmitter, using the metal body of the shell itself as its antenna. broadcasting a continuous signal at roughly 180 to 220 MHz. As the shell flew toward the ground, the reflected echo of that signal would return to a receiver inside the same fuse. The difference in frequency between the outgoing signal and the returning echo, the Doppler shift caused by the shell's closing speed, would produce a low-frequency beat in the receiver circuit. When that beat reached the threshold, corresponding to the shell being within lethal fragmentation range of whatever lay beneath it, a thyrotron tube would discharge a capacitor through an electric detonator, and the shell would explode. The entire decision happened in milliseconds, with no human input after the shell left the barrel. The engineering was, by the standards of 1940, considered impossible. The fuse had to fit inside the nose of a 5-inch naval shell, a volume roughly the size and shape of a pint milk bottle, packed alongside several pounds of high explosive, and offering almost no tolerance for anything to shift or fail. It had to survive the moment of firing, which subjected everything inside the shell to an instantaneous acceleration of approximately 20,000 times the force of gravity. In the same instant, rifling in the gun barrel began spinning the shell at roughly 25,000 revolutions per minute. Every glass vacuum tube in every radio set in the world in 1940 would have shattered instantly under that combination of shock and spin. The fuse also needed a power source. A battery small enough to fit inside a space measured in cubic inches, stable enough to sit on a ship's magazine shelf for months without deterioration, and capable of activating instantaneously at the exact moment of firing. Think about what all of that required simultaneously. The engineers at Section T were not building a radio. They were building a radio that had to survive being hurled from a gun barrel, power itself up from nothing in the first fraction of a second of flight, broadcast a signal using its own metal casing as an antenna, listen for the return echo while being partially deafened by the electromagnetic noise of its own transmitter, process the Doppler shift in that echo against a firing threshold, and make the correct detonation decision in a few milliseconds, all while spinning at 25,000 revolutions per minute inside a milk bottle on a battery that had not existed 10 seconds earlier. That list of simultaneous requirements is precisely why Germany's engineers had concluded the thing was impossible. The Americans who concluded otherwise were not smarter. They were simply willing to dig failed tubes out of the ground until they found one that worked. The Germans had been working on proximity fuse concepts at the Rheinmetall Armaments Company since the 1930s. Their engineers reached a formal conclusion. A fuse rugged enough to survive gunfiring was not achievable with available technology. In 1940, with industrial resources being directed toward Operation Barbarossa, the German proximity fuse program was among those cancelled. The logic was sound by every conventional standard. When your most capable engineers say something is physically impossible, you move resources elsewhere. Tuve's team disagreed. A young physicist named James Van Allen, then 27 years old and newly arrived at the Applied Physics Laboratory, was assigned to the vacuum tube problem. He worked with Raytheon and Western Electric, whose engineers modified the tiny tubes already used in hearing aids to survive the shock of gunfiring, and with Sylvania, which would ultimately produce the overwhelming majority of all tubes used in the program, scaling from 0 to tens of thousands per day across 2 years of continuous refinement. Van Allen and his colleagues developed a method of encasing each tube in a wax and rubber compound that filled every air gap and absorbed the violent acceleration forces. To test whether any given modification worked, they drove to government proving grounds and fired the fuse assemblies upward in specially modified vertical guns, then dug the spent fuses out of the ground by hand and examined each one under magnifiers for failure. A tube that survived became the basis for the next round of changes. This process ran through the spring and summer of 1941, iteration after iteration, until they had a tube that consistently survived the shock. The battery problem was solved by engineers at the National Carbon Company, later part of Union Carbide. They designed what they called a reserve battery, one that did not function as a battery at all until the gun was fired. A sealed glass ampule containing liquid electrolyte sat dormant inside a stack of metal plates. The shock of firing shattered the ampule. The spin of the shell then flung the released electrolyte outward by centrifugal force onto the surrounding plates, instantly forming a wet electrochemical cell that powered the fuse for the brief duration of its flight. Before the gun was fired, no battery existed. The fuse could not accidentally discharge, could not degrade on the shelf, and gave nothing away if an enemy happened to find an unfired round. Multiple safety mechanisms were built in sequence. The fuse would not begin arming until the shell had traveled a specified safe distance from the gun muzzle, preventing any premature detonation that could harm the crew. Full arming required the spin rate to confirm the shell was in free flight. A self-destruct mechanism would fire any fuse that had not found a target within its operational window, ensuring that no live, functioning fuse would ever land intact where an enemy could recover it. By June of 1941, Section T had achieved a successful 5-inch test firing. The project had outgrown the Carnegie Institution. On March 10, 1942, a new institution was formally chartered at Johns Hopkins University in Baltimore, Maryland, built specifically to develop, manufacture, and test the fuse at scale. Merle Tuve became its first director. Under his leadership, the Applied Physics Laboratory's staff grew from 100 to 800 people. The code name chosen for the fuse was deliberate misdirection. Classification officers settled on variable time, abbreviated VT. It looked, on any document or shipping manifest, like a mundane variant designation for the mechanical time fuses already in common use. Nobody reading a supply requisition or intercepting a message would think of a miniaturized radio set. The operational field code, used by artillery units who received the shells, was POSIT. The classification placed on the project was among the most restrictive in the American war effort. The reason was direct. Any dud shell that fell on land and was recovered by enemy intelligence would, on examination of the nose fuse, reveal the complete working principle in an afternoon. The British had recovered a German magnetic naval mine from an Essex tidal flat in 1939, carefully disassembled it, and within days understood it well enough to begin countermeasures. Allied leadership had no intention of giving Germany the same gift. The policy agreed by senior Allied commanders was that variable-time fused shells could be used only over open water, where any dud would sink to depths, making recovery impossible. That policy cost lives that the fuse might have saved had it been released for land use earlier. It remained in force until the German offensive in December of 1944 made the calculus impossible to maintain. The first proof of the fuse's combat value came on January 5, 1943, off the coast of Guadalcanal in the Solomon Islands. Commander William Parsons of the Navy Bureau of Ordnance, the same officer who would later arm the atomic bomb aboard the Enola Gay en route to Hiroshima, had personally escorted the first 5,000 production fuses across the Pacific to New Caledonia. Admiral William Halsey identified 3 ships most likely to face air attack as the initial recipients: the carriers Enterprise and Saratoga, and the light cruiser Helena. Parsons divided the shells and sailed with Helena. On the morning of January 5, 1943, Helena was returning southwest of Guadalcanal from a shore bombardment of Japanese positions at Munda on New Georgia when a formation of Japanese Aichi dive bombers attacked the column. One bomb struck the after-X turret of the nearby New Zealand light cruiser Achilles, killing 13 sailors. As the surviving aircraft withdrew at low altitude, Lieutenant Cochrane, commanding Helena's after 5-inch battery, fired 3 salvos. The second salvo, the first variable-time fused shells ever fired in combat by any nation, killed one of the withdrawing aircraft. The shell had not touched it. It had detonated within lethal fragmentation range because the radio in its nose had received a return echo from the passing metal airframe and made the decision to fire. The operational data accumulated over the following 18 months was unambiguous. American ships firing variable-time fuses in Pacific. Anti-aircraft engagements throughout 1943 needed approximately 155 rounds to destroy one aircraft. Ships firing conventional mechanical time fuses during the same period needed 508 rounds per kill. The new fuse was roughly 3 times more effective under actual combat conditions. This was not test range data, but real engagement numbers from dozens of separate actions across the Pacific theater. Although approximately 1 in 4 5-inch anti-aircraft shells issued to the Pacific Fleet in 1943 carried variable-time fuses, that quarter of the supply accounted for roughly half of all Japanese aircraft destroyed by shipboard gunfire that year. By early 1943, the fuse was being loaded onto destroyers as well as cruisers. The destroyer engagements around the Solomon Islands through the middle of that year provided the most extensive operational dataset the Navy had yet accumulated on any single weapon. and every engagement confirmed the same result. Ships armed with variable time fuses were shooting down aircraft that time-fused ships would have missed. By the end of 1943, American fleet commanders who had begun the Pacific War dreading Japanese air attack were beginning to feel, for the first time, that their anti-aircraft guns were genuinely competitive with the aircraft sent against them. That confidence was not a small thing. It shaped how aggressively American task forces were willing to push toward Japanese island bases, and how quickly the Central Pacific Campaign could be driven forward. The fuse's next decisive test came in the summer of 1944, when Germany began launching Von flying bombs against London in June of that year. The weapon flew at roughly 400 miles per hour at altitudes around 2,000 feet, and before the new fuse was deployed, conventional time-fused anti-aircraft guns were destroying only around 17% of V1s entering the coastal gun belt south of London. General Sir Frederick Pyle, who commanded British Anti-Aircraft Command from the beginning of the war to its end, called that rate inadequate. Engineers at the Applied Physics Laboratory modified the variable time fuse for British 3.7-inch and American 90mm anti-aircraft guns deployed along the English Channel coast, where any dud shells would fall safely into the sea. The documented week-by-week results, reconstructed by historian Ralph Baldwin in his study of the proximity fuse program, showed destruction rates climbing from 24% in the first week of fused operation to 46% in the second week, to 67% in the third, and to 79% in the fourth. On the final day of concentrated Von attacks on England, 104 buzz bombs were detected by early warning radar. 4 reached London. Pyle later wrote that it was the proximity fuse that made possible the near-complete success of the coastal gun line, when the Von campaign shifted to target the Belgian port of Antwerp following the liberation of France. Fresh fuse shipments were flown directly from American manufacturing plants to European theatre anti-aircraft batteries. Over the full defensive campaign at Antwerp from November of 1944 through April of 1945, Allied gun batteries intercepted 2,183 V1s. Of those assessed as immediate threats to the port, 1,766 were destroyed by gunfire. Only 211 reached the target zone. Throughout all of this, the embargo on land artillery use remained. The fear was unchanged. A dud artillery round could lie in a field for hours. Whoever picked it up and handed it to an intelligence officer would have a complete and functioning miniature radio set to examine. Eisenhower wanted the fuse for his field artillery. Patton made his preference known with characteristic directness. The answer from senior Allied commanders was no, not yet. The Germans attacked on December 16. At 5:30 on the morning of December 16, 1944, 3 German armies drove westward into the thinly held American positions in the Ardennes forest of Belgium and Luxembourg. More than 410,000 German soldiers, 1,400 tanks and assault guns, and 2,600 artillery pieces crossed the line of departure in darkness. Hitler's strategic objective was the port of Antwerp. His operational plan required splitting the Allied armies in two and forcing a negotiated peace before American industrial production made the final outcome inevitable. On that same day, December 16, General Patton attended a demonstration of the new posit fuse with his 3rd Army artillery staff. He watched the shells burst above a test target and described what he saw as transformative. He would have occasion to prove that judgment within days. Eisenhower moved quickly to break the secrecy embargo. The anti-aircraft restriction was lifted within 2 days of the initial assault. The field artillery restriction followed shortly after, and the land-use codename POSIT was cleared for unrestricted use against ground targets anywhere along the front. The Army calculated afterward that approximately 200,000 POSIT-fused shells were fired during the Battle of the Bulge in December of 1944 and January of 1945. The effect on German infantry was immediate, and from the German side, completely inexplicable. On Elsenborn Ridge, at the northern shoulder of the German offensive, the 2nd and 99th United States Infantry Divisions held a critical ridgeline against attacks by some of the best formations in the German order of battle, including the 12th Waffen-SS Panzer Division and supporting Volksgrenadier divisions. American artillery on the ridge was concentrated to an extraordinary density, over 300 guns deployed wheel to wheel. Colonel Oscar Axelson, commanding the 405th Field Artillery Group, moved quickly to put the new fuse into action. His 196th Field Artillery Battalion was among the first American units to fire posite shells in the battle. German infantry advancing across the open ground below the ridge discovered what Hocker's men had already found in the pines southeast of Assenois. There was no safe position. The fragments did not come horizontally from a gun line somewhere in the distance. They came down from 30 feet above, and a man in a trench was no safer than a man in the open. The experience was described in consistent terms by German survivors captured in those weeks. Soldiers who had endured Soviet artillery barrages across 3 winters on the Eastern Front said the posite fire was different from anything they had encountered before, not because it was heavier, but because it was inescapable. On the Eastern Front, a man in a deep enough hole survived almost any bombardment. On Elsenborn Ridge, in late December of 1944, men lay in their dugouts and fragments arrived through the gaps in their overhead cover, striking soldiers who had believed themselves protected. The physical geometry of a detonation 30 feet overhead, projecting its cone of steel downward, made every previously safe position unsafe. The most precisely documented single engagement comes from Patton's sector in Luxembourg. The 5th Infantry Division had been pulled from the Saar offensive and rushed north into Luxembourg. On the high ground above the Sauer River near the Luxembourgish town of Echternach, Colonel Robert Bell's 10th Infantry Regiment used posite shells against the 212th Volksgrenadier Division in late December. American artillerymen watched the shells burst 30 feet above German soldiers on bridges and in rubber assault boats crossing the frozen river. The attack broke apart. Patton wrote to Lieutenant General Levin Campbell, the Chief of Army Ordnance, describing the result. His letter, reproduced in the United States Naval Institute's Naval History magazine in August of 1999, reads in part, "The new shell with the funny fuse is devastating. We caught a German battalion, which was trying to get across the Sauer River, with a battalion concentration and killed by actual count, 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first." Prisoner of war interrogation reports compiled by the regiment's intelligence section described the effect of the new fire in a single word: terrific. German soldiers captured after posite barrages across the front described the same experience in similar terms. Throughout January of 1945, they emerged from the fire dazed. They understood they were facing something new. They had no explanation for it. Log-roofed fighting positions that had sheltered German soldiers from Soviet artillery for 3 years were vulnerable to fragments arriving nearly vertically through any gap in overhead cover. No firing position gave reliable shelter, because the threat came from directly above. The word that spread through German frontline units was a phrase meaning tree bursters, rounds that seemed to split open against the tops of the pines and rain steel downward. It was a reasonable inference from what soldiers were observing. It was entirely wrong. During the German offensive, German troops overran an American ammunition supply point containing approximately 20,000 posite-fused artillery shells. It was, potentially, the decisive intelligence find of the entire European war. German ordnance officers had a complete, functioning example of the secret in their hands in a quantity large enough to study at leisure. But Germany's engineers had concluded years earlier, and formally recorded that conclusion, that a radio proximity fuse rugged enough to survive gun firing was physically impossible to build. That conviction prevented them from recognizing what they had captured. The shells were treated as ordinary captured artillery ammunition. They were either fired back at American positions or destroyed. The Applied Physics Laboratory, on learning that a large quantity of posite shells had fallen into German hands, immediately prepared 200 specially designed radio jammers built by laboratory engineer Winfield Salisbury, and installed them in American aircraft in England in case Germany showed any sign of having understood the fuse's operating principle. The jammers were never needed. Germany never detected what it had. German commanders who pieced together their after-action accounts in the weeks that followed never arrived at the correct answer. Frontline troops continued to describe tree smashers as a peculiarity of the Belgian forest terrain, as though the Americans had learned to time their shells for the specific tree canopy of the Ardennes. As the front moved eastward in early 1945 and the fighting shifted to more open ground, German soldiers discovered that the same airbursts followed them out of the forests. Whatever was causing the shells to burst above them was clearly not related to the trees. They still had no explanation. Hermann Göring confirmed Germany's fundamental failure to understand the technology in a formal interrogation at Augsburg on May 10, 1945, 2 days after VE Day. General Karl Spaatz, commanding United States Strategic Air Forces in Europe, asked him directly whether he had any knowledge of a proximity fuse. Göring replied that yes, in 3 or 4 more months there would have been German production. He added that he did not believe Japan possessed the design because Germany had not shared technology with its allies that had not yet reached production status. The second-ranking man in the Third Reich believed, 2 days after Germany's unconditional surrender, that the proximity fuse was still something Germany was working toward. The Allies had been firing it against German forces for over 2.5 years. To understand why Germany failed so completely to close that gap, you have to understand the difference between the two countries' approaches to solving hard engineering problems under wartime pressure. Germany's proximity fuse effort was not small. By 1944, the German military had funded more than 30 separate programs, pursuing different technical approaches, and some post-war evaluations put the number as high as 50. They pursued acoustic fuses triggered by engine noise, infrared detection fuses, photoelectric fuses, and multiple different radio frequency designs. Each was managed by a separate contractor. Each was held in a separate security compartment with minimal information sharing between programs. The result was that no single approach received enough concentrated engineering talent or industrial resources to reach production. There is one further fact about the German effort that deserves to be stated clearly. Germany was not decades behind. The electrostatic capacitance fuse, being developed at the Rheinmetall Armaments Company by 1944, had achieved promising reliability in testing at close range and was approaching production readiness when Allied forces overran the factories in the spring of 1945. Germany was not stopped by a lack of engineering talent. It was stopped by fragmented organization, resource competition between more than 30 parallel programs that could not share knowledge across security compartments, and the cascading effect of the 1940 cancellation that had cost 4 years of development time that could never be recovered. Consider what that means in practice. A Rheinmetall engineer who had a promising proximity fuse design in the autumn of 1944 could not walk it across a courtyard to a general and ask for a production decision. He submitted a report to his department head. The department head submitted it to the relevant ordnance office. The Ordnance Office compared it against the designs already funded in the other 29 or 49 competing programs, none of whose engineers were permitted to talk to each other. If the report survived that review, it went upward again. By the time a decision came back, 6 months might have passed, the war situation might have changed entirely, and the engineer might be working on something else, because his original project had been defunded in a resource reallocation he knew nothing about. The German proximity fuse programs did not fail because Germany lacked clever engineers. They failed because the organizational architecture that surrounded those engineers made it structurally impossible to concentrate brilliance long enough to finish anything. In Germany, technical innovation moved vertically. A researcher submitted a proposal upward through an ordnance office. The office reviewed it against existing doctrine and forwarded it, or did not, to the next level. Ideas that survived returned downward as directives. Each level of review consumed weeks or months. The man doing the actual work at the bottom of the chain had engineering talent. What he did not have was a short path to the person who could say yes, build it, and start production next week. The Americans operated differently, and the proximity fuse is the clearest illustration of how. Merle Tuve, given his mandate in August of 1940, spent the following year working directly with vacuum tube manufacturers and driving to government proving grounds to fire test fuses and dig them out of the ground with a shovel, iterating through design modifications on a timeline measured in weeks rather than months. When the Navy needed to decide in early 1942 whether the fuse was ready for mass production, 5 manufacturers began production simultaneously within days of the demonstration. A physicist showed that it worked. The order was given to build it. The production challenge that followed was, in some ways, as difficult as the engineering. A single fuse contained approximately 130 components, including 5 vacuum tubes, a reserve battery, a thyrotron firing tube, a safety and arming mechanism, and enough wiring to connect them all inside a space the size of a pint bottle, while surviving both the shock of firing and the spin of flight. Every component had to meet tolerances that American industry had never previously applied to an artillery round. The Crosley Corporation in Cincinnati, Ohio, which had been making consumer radios and appliances before the war, was among the first 5 companies contracted to assemble fuses in early 1942. Its engineers spent the first months discovering that components which worked perfectly in a laboratory failed intermittently on the production floor because of slight dimensional variations that would have been acceptable in any previous application. The quality control standards developed at Crosley and its partner plants during 1942 became the manufacturing baseline for the entire program. Within a year, those standards were being applied by dozens of firms that had never built a piece of ordnance in their lives. 5 companies began production in 1942. By the end of 1943, 40,000 fuses were leaving American factories every day. By the war's end, the daily output had reached 70,000, assembled by 87 firms across 110 facilities. The total production run reached approximately 22 million fuses at a cost of just over $1 billion in 1940s money. Among those manufacturers was the Wurlitzer Corporation in North Tonawanda, New York, whose barrel organ factory had spent the 1930s building pipe organs and jukeboxes and now assembled pencil eraser-sized vacuum tubes into miniature radio sets destined for artillery shells. The primary vacuum tube production line was at a General Electric facility in Cleveland, Ohio, converted from the manufacture of Christmas tree lamp bulbs. Each completed fuse contained approximately 130 components, including 5 vacuum tubes, and every one of those tubes had to survive 20,000 times the force of gravity and maintain its calibration while spinning at roughly 25,000 revolutions per minute. The organizational culture that produced that output was the same culture that had never accepted the German engineers' formal conclusion that the thing was impossible. That disposition, the willingness to treat a stated impossibility as an engineering problem waiting for whoever was willing to dig tubes out of the ground long enough, was as important to the outcome as any single technical insight. Merle Tuve returned to pure physics research after the war. He spent his later career studying the Earth's interior through seismological analysis and making contributions to the understanding of atomic nuclei. He gave few interviews about his wartime work. He died in 1982. His name appears in no account of the Battle of the Bulge. James Van Allen, who had learned to keep a glass vacuum tube alive at 20,000 times the force of gravity by examining hundreds of failures at government proving grounds, returned to cosmic ray physics. In January of 1958, the American satellite Explorer 1, launched from Cape Canaveral in Florida, detected a vast belt of charged particles trapped by the Earth's magnetic field, extending thousands of miles into space. Those belts carry Van Allen's name. The young physicist who solved the fuse's vacuum tube problem helped open the space age. The technical infrastructure built at the Applied Physics Laboratory to miniaturize and harden electronic components for artillery shells did not disappear when the war ended. The engineers who had learned to make a vacuum tube survive 20,000 times the force of gravity spent the late 1940s learning to make a guidance system survive a rocket launch. The skills transferred directly. The institutional culture of moving from a physicist's first successful test firing to mass production in months rather than years transferred directly. The proximity fuse program did not just produce 22 million fuses, it produced a laboratory whose capabilities would define American weapons development for the following generation. The Applied Physics Laboratory did not close when the war ended. It continued directly from proximity fuse work into guided missile development, producing America's first naval surface-to-air missiles through a program called Project Bumblebee, which yielded the Terrier and Tartar systems that defended American carrier groups through the 1950s and 1960s. The principle at the center of the variable time fuse, a miniaturized sensor that could make an autonomous decision in flight, became the foundational principle of every guided weapon that followed. Modern artillery proximity fuses use the same Doppler radio principle that Tuve's team established in 1941, now implemented in transistors and integrated circuits rather than glass tubes, settable electronically in seconds. American field artillery used airburst fuse fire extensively in Korea and Vietnam, where the tactic of walking a proximity-fused barrage around an attacked perimeter became standard doctrine for defending forward bases. The mission is unchanged from what it was in the pines southeast of Assenois. The shell senses its own proximity to the target and decides for itself when to explode. Rear Admiral Louis Strauss, who would later chair the Atomic Energy Commission, assessed the fuse's place in history in his memoir Men and Decisions, published in 1962. He wrote, "While no one invention won the war, the proximity fuse must be listed among the very small group of developments, such as radar, upon which victory very largely depended." Hans-Kurt Hoche was captured in the spring of 1945 and composed his manuscript in American custody later that year and the next. In all the available post-war literature, there is no record that anyone told him what had actually destroyed his battalion southeast of Assenois. The proximity fuse, the reserve battery shattered by the shock of firing, the Doppler receiver making its millisecond decision, none of it appears anywhere in his account. He died having recorded that those shells were tree smashers, produced by Americans with improbable timing, and that incomplete explanation was the best the German military ever offered. 22 million times, an artillery shell left an Allied gun with a small radio station in its nose. 22 million times, that station broadcast its signal outward, listened for its own echo, and made a decision. The decision was not made by Tuve, and not by Van Allen, and not by the engineers at Sylvania or the barrel organ factory in North Tonawanda. It was made by the shell, in the air, in milliseconds, alone. That was what Hoche heard above his column in the Belgian forest on December 30, 1944. That was what Goering was unable to account for 2 days after Germany's surrender. That was what more than 30 German research programs, applying some of the finest ordnance engineering in Europe, had formally concluded was physically impossible to build. A 39-year-old physicist in Washington and a 27-year-old physicist who would one day discover the Earth's radiation belts had disagreed. The war turned in part on that disagreement. Thank you for watching this all the way through. If this story stayed with you, hit the like button. It is the most direct way to help this kind of history reach the audience it deserves. If you are not subscribed yet, now is the right time. Hit subscribe and the bell, and you will not miss the next one. I would like to know where you are watching from today. And if someone in your family served in World War II, a grandfather or grandmother, a great-uncle, someone who worked in a factory assembling something without ever being told what it was for, tell me about them in the comments. Their stories belong here. Thank you. See you in the next one.